Swayam Prabha. Digital India. Educated India.
So, where does weak duality come from? So, suppose now let us say let x star be, so I will call this problem P, okay. Let x star be an optimal solution of P, and optimal solution of, let x star be an optimal solution of P, and now let us look at lambda of x star comma this, okay. So, this is equal to f of x star plus all this, I going from 1 to m for the inequality constraints and j going from 1 to p for the equality constraints. Now, what is it that you can observe here? So, if you look at this term here, these two terms, what can one say about these? Well, x star is an optimal solution of P. Okay. If it is an optimal solution of P, then it has to at the very least it has to be feasible, which means that j of x star has to be equal to 0, which means this term is actually 0. Okay. All these guys, this term here is actually 0. Okay. All right. What about this term here? What about gi of x star? Well, gi of x star being, again x star being feasible, it means that this guy is less than equal to 0. All right. Now, if this guy is less than equal to 0, then so we have that, then that f of x star is greater than equal to lambda I times something that is less than equal to 0. Now, I have not yet said anything about lambda I itself. Okay, I have not told you that lambda I should be greater than equal to 0 or anything like that. We did put lambda I greater than equal to 0 in this optimization here when we were defining the dual problem. So, let us go ahead with that. So suppose we restrict lambda I to be greater than equal to 0 for all I equal to 1 to m. Then in that case, what would we get? Then we would get that this here, okay, is less than equal to f of x star. All right, we would get that this is actually less than, so this quantity here is less than equal to f of x star. Why? Because this is less than equal to 0, this is less than equal, because the GIs are actually less than equal to 0 and these terms have disappeared. Okay. So, let us play around with this in a different sort of way. So, suppose x star is the optimal solution of P. All right. Now, if, and this is this is the value of my Lagrangian. Now, remember remember that d of lambda comma theta is actually the infimum of the Lagrangian. So, d of lambda comma theta is therefore always greater than equal to L of x star comma lambda comma theta. All right. So, d of lambda comma theta is greater than equal to L of x star comma lambda comma theta, right. So, if this is, oh, sorry, my mistake here. So, d of lambda comma So, d of lambda comma theta is the infimum of the Lagrangian. So, if it's the infimum of the Lagrangian, it follows that d of lambda comma theta is always less than equal to L of x star comma lambda comma theta, and this holds for all lambda and for all theta. This is just, I do not even need to restrict my sign here. This holds for all lambda and all theta, right. Now, what does this mean? And this quantity L of lambda x star comma lambda comma theta was itself less than equal to f of x star. So, and in getting to this inequality, we needed that lambda is greater than equal to 0 and theta is in Rp. So, for when lambda is greater than equal to 0 and theta, and for any theta, we have that d of lambda comma theta is less than equal to f of x star. So, this is true for all lambda greater than equal to 0 and all theta and all vectors theta. What does this mean? You look back here then again at this optimization. What is this optimization? Well, it has a maximization of d of lambda comma theta over precisely the lambdas and thetas that are mentioned here. So, what does this mean? It means then that the maximization of d of lambda comma theta over lambda greater than equal to 0 any theta also has value less than equal to f of x star. And now, what's this f of x star here? Remember, x star was an optimal solution of P, right. It was an optimal solution of P. So, this is in fact the optimal value. So, this here is an optimal value of P, optimal value of P. And what is the one on the left hand side? Let us call this problem D. The one on the left hand side is simply the optimal value of D. And what have we got here then? We have got that the optimal value of the dual is less than equal to the optimal value of the primal. So, this statement here is nothing but the statement of weak duality. So, what does this mean? To summarize, you can take any optimization problem like this, you write its Lagrangian. Lagrangian is formed by taking a linear of the objective and a linear combination of the constraints. Then for the constraints that are inequality constraints, you restrict the multipliers, the Lagrange multipliers here to be greater than equal to 0. For the constraints that are equality constraints, you do not need to have any such restriction. Then you look at the least possible value of the Lagrangian over the entire space, define that as d of lambda comma theta, and then maximize that d of lambda comma theta over the Lagrange multipliers the way you have restricted the Lagrange multipliers, lambda to be greater than equal to 0 and theta can be anything. In that case, and then what do we get? We get that the optimal value of this is what we call the dual problem. You call this the dual problem, you call this the primal problem. Okay. What we get is weak duality. So, the optimal value of the dual problem is always less than equal to the optimal value of the primal. All right. Okay. So, now I will show you now that actually what you found calculated as the dual of a linear program in fact appears as a special case of this. So, that is not very hard to see. So, let's just go through this. So, consider a linear program in standard form C transpose x, Ax equal to b and x greater than equal to 0. Now, I am going to create a Lagrangian of this lambda of L of x lambda comma comma theta. Now, let us be careful here, lambda corresponds to the inequality constraints. So, that is what is going to, so lambda is going to multiply my x and theta corresponds to the equality constraint. So, theta is going to multiply my ax minus ax equal to b, and since we want it in this in the form that we had for the optimization problem on the previous page. So, what I will write this as ax minus b equal to 0. Okay. So, this is now, so my Lagrangian therefore is C transpose x plus theta transpose ax minus b. Now, if you go back here, I wrote this this problem with inequality constraints only, since now, but now I am going to allow for equality constraints here in sorry, I am going to allow sorry, I wrote this problem with less than equal to constraints here. So, if you go back to this problem, this problem has been written with less than equal to type constraints, whereas here my constraints are a greater than equal to type of constraint. So, I can effectively just multiply both sides by -1, and that would flip the direction of the inequality of the constraint. Alternatively, I can, what I need to do is just compensate for that in the definition of my Lagrangian itself. So, this is now my Lagrangian. Now, let me write the dual function which is d of lambda comma theta, that is the infimum of the Lagrangian over the entire space. Now, if you look at the Lagrangian function as a function of x, if you look at this as a function of x, this is clearly a linear function in x. Okay, for each fixed lambda and theta, this is a linear function in x. And what you are doing here is you are taking the infimum of this linear function over this entire space. Now, a linear function, if you minimize this over in an unconstrained, without any constraints, then you would get the optimal value is going to be minus infinity, except in the case when the coefficients of the linear function are actually 0. The coefficients if the coefficients involved are 0, then the linear function would evaluate to something that is just a constant. So, now to do that, to evaluate this more clearly, let's just gather together the coefficients of x. So, let's write this L of x comma lambda comma theta in this sort of way. C minus A transpose theta minus lambda, the whole thing transpose, EC plus this, the whole thing transpose x, then there is and then I am left with a minus theta transpose b. Okay, all right. So, now if I take the infimum of the Lagrangian, then that tells me that d of lambda comma theta should be equal to one of these. So, it is equal to either minus theta transpose b if C plus A transpose theta minus lambda is exactly equal to 0, and otherwise it is minus infinity. So, whenever this is not equal to 0, you can choose a suitable x to drive the value down to minus infinity, right. So, it is equal to some real value which is minus theta transpose b for x for those so long as theta and lambda satisfy this equation, otherwise it is equal to minus infinity. Right. So, now if I am looking, if I now look to maximize d of lambda comma theta, Remember, now I need to do this over lambda greater than equal to 0 and over all theta. Then where would my maximum be attained? Well, my maximum cannot be minus infinity, obviously, since it's a maximum. So my maximum is going to be attained over this region. What do you mean by this? What do I mean by this region? I am looking for the maximum over the lambda comma theta such that they satisfy this, right. So effectively, the maximum is going to be equal. This is going to be equal to maximize minus of theta transpose B subject to C plus A transpose theta minus lambda equal to 0, lambda greater than equal to 0 and any theta. Now, if you play around with this a little bit, what do you realize? If you play around this with play around this with a little bit, you realize that, well, my lambda doesn't appear in the objective at all. I can absorb this, the fact that lambda is greater than equal to 0 and there is a minus lambda here, then it's simply that the lambda is simply appearing here as a slack variable. So effectively, this constraint here can be written in this form, that I can simply write this as maximizing minus theta transpose B C plus A transpose theta greater than equal to 0, and my theta is unrestricted. So my lambda plays no role. Lambda can be removed from this by just observing that these two equations here are effectively saying C plus A transpose theta equals lambda and lambda is greater than equal to 0, right. So it's maximizing this bit. So I can simplify this even further and write this more neatly. So I can say maximize minus of theta transpose B C. So I'll write this in a following way. I can C is greater than equal to negative of A transpose theta. Okay. So now, and I am maximizing over theta. Now notice how something that we can do. Since theta has no sign constraints, maximizing this particular thing, minus theta transpose B is subject to C greater than equal to minus A transpose theta. This can be since theta has no sign constraints, I can just replace theta by minus theta, and the optimization problem would remain, optimal value would remain, should remain the same. Or alternatively, I take this minus sign, I just define theta dash as minus theta, or define y as minus theta here. If I just let y equal to minus theta, then what I have is our familiar form of the dual, which is maximize B transpose y subject to A transpose y less than equal to C. Okay, remember, I am not multiplying anything by a negative sign. I am just changing my notation. I am doing a change of variables. I am expressing y as I'm expressing minus theta as y and then substituting, and that gives me this. And this is actually nothing but the familiar dual problem of this particular problem. So this was our primal, and this is what we had learnt as the dual. Okay. So if you work with the Lagrangian and you follow this, follow the routine that I mentioned on the previous slide, you get back the dual. Okay. So what this does is this way of this entire whatever is there here, right, on the that is mentioned here, which is that you define the Lagrangian, you then define the dual function by taking the infimum of the Lagrangian over the whole space, and then maximize the dual function subject to with constraints on the Lagrange multipliers. If you do all of that, that actually gives you if you do that for a linear program, that gives you back the dual that we had defined earlier. So, this way of defining the dual is now is a way of is basically generalizing the duality formulation of for linear programming to problems that are potentially non-linear. Okay. So, this is going to be our vehicle for analyzing the for talking of duality for convex optimization. Okay. I should also tell you that there is another connection here. Let me mention that. So, there is another the word dual is one that is being used by multiple people in different senses. So, there is another dual which is called the conjugate dual or conjugate dual, or what is also called the Fenchel dual, thanks to Werner Fenchel. Okay. So, what is this dual? This dual is of the conjugate dual of a function f. Okay. F is denoted in of a function f. It is denoted as f star. So, f star of y is defined in this way. It is defined as the supremum over all x of y transpose x minus f x. Okay. So, what you do is you subtract from f subtract f from a linear function whose slope is the parameter that you control. The slope here is y. So, you subtract f from this linear function and you look at the maximum value of that you can get with a certain slope. So, what is the maximum departure of this function from a linear function, and study that as a function of the slope. That if you look at that as a function of the slope, that quantity is what is called the dual function. Now, the dual function, just like d is has the d was always concave, then this f star is always convex. Right. And so now what is the connection between d and f star? Well, there is a connection in the following sense, that you can see that this here as a what you are taking the supremum of has a resemblance to the Lagrangian in some way, has a resemblance to the Lagrangian. So it is sort of closely related to an optimization to a certain type of optimization problem, and that optimization problem is basically, you can consider the optimization problem where you are minimizing f. If you are minimizing f subject to say x greater than equal to 0. All right. So, in that case, the kind of quantity you would encounter would end up becoming something like this. But this is just for you to mention, for you to know, there is no this is another notion of the dual, and it should not be confusing this with the Lagrange dual. All right. Okay. So, what we will be working with is the Lagrange dual.